Okay, so good morning, everyone. As they said, that my name is Didac. I'm going to present the beginning of my research under the supervision of Michel Perrier, Professor Michel Perrier at the Polytechnical School of Montreal, and Dr. Boris Tartakovsky, researcher at the National Research Council of Canada in Montreal. So the model, first, I'm going to present a control-oriented dynamic modeling of a microbial fuel cell, a topic which I see it's quite different from all the other topics presented so far in this conference. And we call it Combined Bioelectrochemical Electrical Model of a Microbial Fuel Cell. I'm going to explain later why. So why do we need another dynamic model? There are already bioelectrochemical models developed which are able to describe those long-term dynamics of microbial fuel cells when they are operated at a constant or at a always connected external resistance. However, in our laboratory, we've been experimenting with intermittent connection of the external resistance. That means that we open and close the circuit intermittently so we can observe fast dynamics, which cannot be described by those bioelectrochemical models. And an example of that would be pulse width modulated operation. I'm going to explain later what that means. And this kind of fast dynamics, they can be described by equivalent electrical circuits. The only problem is that those equivalent circuits, they don't contain the microbial dynamics that describe those long-term effects. Therefore, we observe that the need to describe, to develop another dynamic model which is able to describe both long-term and fast and short-term dynamics. Or, well, as I said, so electrical, short-term due to the electrical components in the MFC, and long-term due to the biological part of the MFC. So the objective is to be able to describe this double-layer capacitance effect and those complex nonlinear dynamics that we observe during the intermittent connection of the external resistance. And also, we would like to simulate the capacitance effect of the anodic biofilm on the MFC performance. So the modeling approach, first, I'm going to explain what's the pulse width modulated operation. So you can see, so the pulse width modulated operation of a microbial fuel cell, it's characterized by its duty cycle. That means that, as I said, we are connecting and disconnecting periodically the external resistance. We go from a low value of the external resistance to infinite, open circuit, and that's characterized by its duty cycle. That's the ratio between the time where the external resistance is connected divided by the period of time multiplied by 100, that's in percentage. So, for example, all the experimental results I'm going to show, we've been operating at a frequency of 0.1 Hertz. That means a period of 10 seconds, a duty cycle of 95%. That means that in 10 seconds period, we are closing the external resistance, we are closing the circuit during 9.5 seconds, and half a second, the circuit is open. So this results in different time scales. When we see, for example, voltage versus time, we can see very short-term dynamics, those blue lines, blue peaks that come from, they are typical charge and discharge behavior profile of a capacitor. And we have these long-term dynamics that come from the biological part of the, so just point that these short-term dynamics are from seconds to milliseconds, while these biological long-term dynamics can change from hours to days. So yeah, that's quite a nice dynamics. So first, short-term dynamics, as I said, we can represent them by an electrical equivalent circuit. That's the typical circuit we've already seen before in the other presentations. So we have the switch, the external resistance, voltage of the cell that we can measure, and the current. So we use an equivalent circuit. In this case, we're using the dynamic equations of the circuit. We have a capacitor and the voltage of the capacitor which represents the capacitance of the biofilm, one internal resistance in parallel to this capacitor, which is always associated to the activation over voltage, and as a resistance in series with those two elements, which is usually associated to the ohmic over voltage and the electrical source of energy. So then we have bioelectrochemical models. In this case, we are considering the one developed or presented by Pinto in 2010. So this model describes the anodic biofilm, the anodic compartment, let's say. So, and assuming a non-limiting cathode. So it's a two-population microbial fuel cell model where we consider electricigenic bacteria and methanogenic archaea. We always consider acetate as substrate, also as a carbon source. And, well, some assumptions for this model, we consider multiplicative monokinetics. We assume that there's an intracellular mediator, for example, NADH. We are not modeling gradients in the biofilm. We take into account the effect of the biofilm, but we are not assuming, we are not considering gradients of carbon source or microbial populations. And finally, we consider a constant pool of this intracellular mediator per microorganism. So yeah, so we have the equivalent circuit and the bioelectrochemical circuit. So why not complement the equivalent circuit using the equations of the bioelectrochemical model that generate this current that is going through the equivalent circuit? So that's what we call combined bioelectrochemical electrical model of a microbial fuel cell. So this model can be described, as always, by dynamic equations. So in this case, I'm considering macroscopic mass balances. So we just consider the MFC. Accumulation, for example, in this case, substrate or acetate inside the reactor, the accumulation is equal to what goes in minus what goes out. For example, substrate consumption by the bacteria, transport in minus transport out. The same for the microbial populations, growth of the bacteria minus decay. In this case, this term represents the effect of the biofilm. So there's a space limitation, so bacteria cannot grow until infinite concentration. That makes no sense. So we are taking it into account. And the same, an intracellular mass balance for the oxidized mediator. Finally, so the equations that we are adding is the voltage at the capacitor. So we can, applying those normal Kirchhoff's laws in the circuit, we can find the voltage at the capacitor. So we are combining those two, all the equations together, so we have the effect, the capacitance effect. Then, again, you already know an electrochemical balance. In this case, the current produced by the cell, we have this voltage of the capacitor. And finally, there are some of those electrical variables that we don't know very well how to model them. So we are just using empirical equations for the open circuit voltage, capacitance, and internal resistances. Just say that those empirical equations, they just describe what we can observe, which is usual, so that the capacitance, for example, is very low when the biofilm is under development, and it's large, it's a very high value of the capacitance when the biofilm is fully developed. So the opposite for the internal resistance, very high at the beginning, very low when the biofilm is fully developed. So as any dynamic model, we need experimental results to compare it to. So the experimental setup we were using is a small 50 milliliters air cathode membraneless MFC. We are using carbon felt anodes with this cathode. And important, we are assuming continuously fed microbial fuel cell with recirculation. I forgot to mention that all the mass balance equations are for a continuous stirred tank reactor. The experimental inputs, so the flow rate, so we can see changes, but it's an input flow rate that keeps the hydraulic retention time at around 7.5 hours. Influent concentration, we perform stepwise changes from substrate deplete zones to substrate deplete conditions, so from low concentration to very high concentration. And the external resistance, here I'm only showing the low value, so it goes from here to infinite and in a periodic way. So the low value was around 12 ohms. Additionally, because we have this dynamic equation of the equivalent circuit, we can solve it analytically, and we can, well, someone else, a previous student in Coronado last year, he developed an online estimation procedure able to estimate online the open circuit of the voltage, so it's around 0.35 volts, the capacitance at the capacitor, it's around 0.75 farads. The internal resistance one, the one associated with the ohmic losses, around 3 ohms. And the internal resistance 2, the one associated with the activation losses, from 5 to 30 ohms. So I'm going to use all those data also. So there's 2 approaches for this model. I can use all the equations, the fundamental equations based on mass balances and electrochemical balance, as well as those empirical equations for the electrical variables. I'm giving input flow rate, input substrate concentration, and external resistance to the model, and he describes the output substrate and the voltage of the cell. If I use this online estimation data, I can replace those empirical equations, I can neglect them, and use directly the values obtained from the experimental voltage measured. So online estimation, and I give them to the fundamental equations. Again, I'm obtaining the output substrate concentration and the voltage at the cell. So if we compare the fitting of those 2 approaches of the model, so here we have the simulation, the one that considers all the equations, and here we have the prediction model. So at the top plot is substrate, so dotted line is the input substrate profile, red dots is the experimental data, and the solid dark line is the output of the model. Here I have the voltage at long term, so here I'm showing only the average voltage. I'm not showing, because otherwise the profile is going to be something with very fast dynamics, and I'm focusing only on the short and on the long-term dynamics, so we can see that the simulation model follows the trend, although there are some dynamics that cannot be modeled. And the short term, so here we would have seconds, and here that's the voltage, so we have those peaks typically from charge and discharge of a capacitor. Again, we see that we can follow the trend, but it's not very optimistic result. Well, and we can estimate some parameters with an interval of confidence of less than 5%. The prediction model, however, if we consider this online estimation procedure, we can see that for the output substrate concentration, the fitting is quite better. The long-term profile for the voltage is much better than this one, and as well as the short-term prediction of the voltage. In this case, we can estimate some of the parameters with a confidence interval of less than 15%. That's typical in prediction models. So we have a very useful tool. I was saying that the simulation model can follow the trends, but we can use it to, even if it's not that accurate to the experimental results, we can use it to see what's the capacitance effect on the MFC performance. So we consider 3 different modes of operation. In this case, after a perturbation, a 50% decrease in the input substrate concentration. So we have here delta T. So at time 0, I perform, on a step change, decrease 50% substrate concentration. And operating the external resistance at an optimal external resistance, here we use typical maximum power point tracking algorithms. So we track the maximum of the power curve, that's the blue line, at an optimal external resistance, because this is an electrical system. We already know that maximum power is found when the external resistance equates to the internal resistance. So that's what these MPPT algorithms do. We can assume a duty cycle of 100%. So that means that we consider always closed the circuit at a value of the external resistance which is far from being the optimal. So when we perform this decrease in the input substrate concentration, there's a sudden drop in the power produced, which is normal because the external resistance is not optimal. Finally, if we perform a PW operation that we open and close the external circuit with a duty cycle of 95%, again, so closing during 9.5 seconds and opening only for half a second, and with the low value of the external resistance exactly the same as the one operated continuously. So we can see that this is the average power produced. We can model, or the simulation gives very similar results to the power output when it's operated with the optimal external resistance. So we don't need to track the external resistance apparently when we operate intermittently the external resistance. And again, this is a simulation, but we have observed the same results which are already published in other papers experimentally. So finally, conclusions. This model is a useful tool. We can describe the complex behavior of these MFCs operated at at varying conditions of the input substrate concentration. And it can be used, it can be oriented to control, to the development of control strategies for MFCs. If we benefit from the online estimation of the electrical variables, we can accurately predict both effluent concentration and output voltage produced by the MFC. And this simulation model is able to reproduce the biofilm capacitance effect on the MFC performance. So the future work I'm going to do is so the final goal would be to develop model-based control strategies, focused in this case regulation and disturbance rejection. So for example, I want to keep the output substrate concentration below a certain threshold, but we can have disturbances in the input substrate concentration. So I need to develop a controller which is able to keep it at below this threshold. But the problem, as you already know, is that we cannot measure online the output substrate concentration. So I would need to design software sensors using this model capable of estimating this effluent concentration online. So that's what we usually call in control as observers. So finally, for those who are more interested in modeling, dynamic modeling of microbial field cells, so this Pinto is the one, so the bioelectrochemical model, intermittent connection and PW connection of MFCs, those two papers here. Online estimation of those electrical variables was published at the end of last year. And the parameter estimation for this combined bioelectrochemical electrical model is going to be published soon. I think it's in June. Well, I'm going to the Mediterranean Conference on Control and Automation. And yeah, so all the equations of this model will be published there, and also the estimation procedure used for estimating some of the parameters. So thank you very much.
So this is just for the video you have to...
No,
just
well, honestly, I'm not sure. I think it's too large.
A control question.
Yeah.
In fact, two questions. Have you considered, I spoke to you previously, have you considered going for a reduced, you get a complex system, then you go to the reduced system, where you consider selected variables, parameters in other words, we're talking about parameter estimation. You consider a selected number of parameters which may influence the microbial fuel cell. And then the second one is, have you considered least squares?
That's okay. So for parameter estimation of any model, we need to select those parameters that influence the most the output. For that, I didn't talk about that. I'm using those sensitivity functions, the derivative of the outputs with respect to each one of the parameters. And because it's a dynamic model, it's a little bit more complex. And you use this Fisher matrix information for it. But so yeah, I mean, there are a couple of parameters. Maximum substrate consumption by the electricity bacteria. This is one of them, which influences a lot the output. And the other one would be the mediator yield, the intracellular mediator yield. Well, it's one of the parameters. And yeah.
And what about considering a least square or minimization?
That's for sure. But in order to get the value of the parameters, we have to estimate them. So I have to minimize the error between the experimental values and the output of my model. Yeah, but that's not at least, well, I'm minimizing the square of the error, but that's a non-linear dynamic
That's correct.
Optimization problem. So it's a little bit more complex.